I'm sure many of you have seen this in your chemistry lab, right? You take a light blue solution of a copper salt, you add a little bit of ammonia, and poof, suddenly it turns into this gorgeous, deep royal blue color. It's a very common experiment, isn't it? But have you ever stopped and thought, what is really happening there? I mean, at the molecular level, why does that specific, dramatic color change happen? Well, the answer to that puzzle lies in one of the most important ideas in all of inorganic chemistry, Werner's theory of coordination compounds. This is the theory that helps us make sense of all these strange observations, just like the one we just saw. And believe me, it's the key to understanding a huge, huge part of transition metal chemistry. You know, before the brilliant work of Alfred Werner, things like this color change were a complete mystery. Chemists could see that metal salts were forming new, stable compounds with molecules they shouldn't even be reacting with, but they just couldn't explain how or why. It made this entire area of chemistry very, very confusing. So, let's look at the core problem they were facing. Take a compound like cobalt-3 chloride, that's CoCl3. Now, according to the simple ideas about charge, this should be perfectly stable and happy. But when you mix it with ammonia, NH3, it forms a completely new, very stable substance, something like CoNH3,5ClCl2. Just look at that formula. Why on earth would a neutral molecule like ammonia want to bond so strongly to cobalt, and why exactly 5 of them? The older classical theories of bonding, they just had no good answer for this. And this is where Alfred Werner comes into the picture. Around the 1890s, he came up with a revolutionary idea. It was so simple, so elegant, and so powerful that it solved the mystery completely and, laid the foundation for all of modern coordination chemistry. So, here's his brilliant idea in a nutshell. Werner said that a central metal atom doesn't just have one type of bonding capacity, it has 2. This single idea changed everything. So what are these 2 types of bonding? Let's take a look. Okay, so on the left, we have the primary valence. Now, this one is something you are already familiar with. It's simply the oxidation state of the metal. Its only job is to balance a positive charge of the metal ion with some negative ions. Simple enough? But now, look to the right. This was Werner's new idea, the secondary valence. This, he said, was a fixed number of points around the metal where other molecules or ions, which we now call ligands, must attach. And this fixed number is what we call the coordination number. Right, so the crucial point is this. Primary valence is satisfied only by negative ions, and it's non-directional. It doesn't care about the shape. But the secondary valence, this can be satisfied by any species that can donate an electron pair. So it could be a negative ion or even a neutral molecule like water or ammonia. And here's the most important part. This secondary valence is directional. It actually forces the ligands into a specific, fixed, 3-dimensional shape, like an octahedron or a tetrahedron. Now, this is the #1 point of confusion for students, so let's make it very, very clear. Oxidation state, that's your primary valence, is all about the charge of the metal ion, but the coordination number, the secondary valence, is a totally separate concept. It's about geometry. It's about how many fixed positions around the metal need to be filled by ligands to make the whole structure stable. They are 2 different numbers describing 2 very different things. To make this new idea of 2 valencies a little easier to understand, let's use a simple analogy. Just think about how our solar system is organized. I want you to imagine a tiny, tiny solar system with a sun in the middle and planets orbiting it in fixed paths. That's basically what a coordination compound is like at the molecular level. So the central metal ion is like our sun, the big, massive object at the center that holds everything together. The ligands, they are like the planets. And just like how planets don't just float around randomly, but are locked into fixed, stable orbits, in the same way, the ligands are locked into fixed positions around the metal. The secondary valence is like the rule, or the force that decides what these stable orbits are, and the exact number of planets the sun can hold. This one powerful idea completely revolutionized chemistry. Suddenly, it all made sense. It explained why these strange compounds have fixed formulas, fixed shapes, and their own unique properties. It turned a confusing mess of observations into a structured, predictable science. And for this incredible breakthrough, Alfred Werner was awarded the Nobel Prize. All right, so we have the theory. Now let's try to build a very clear mental picture of what is actually happening at the molecular level when one of these coordination compounds is forming. So, picture a central metal ion just floating in a solution. It's positively charged and it has empty orbitals. You can think of these like open hands, ready to accept something. Now imagine some ligand molecules approaching it. Each ligand has a pair of electrons that it's ready to donate. Think of it like a little gift. The ligand offers this electron pair gift to one of the metal's open hands. The metal accepts, a strong coordinate bond is formed, and that ligand is now locked into place. This happens again and again until all the metal's secondary valencies, all its open hands, are full. And what you get is a stable, beautiful geometric structure. Now, this theory isn't just something for textbooks. Oh no. It explains things we see in the lab every single day and is even used in life-saving medical treatments. So, remember that light blue copper solution from the beginning? Let's finally solve that mystery. Initially, the copper ion in the water is surrounded by, or coordinated to, water molecules. The complex is CuH2O4 and it is this complex that gives the solution its light blue color. But when you add ammonia, you see the ammonia molecules are better ligands. They form stronger coordinate bonds. So what do? They push the water ligands out of the way and form a new complex, CuNH342+. This new arrangement of ligands changes how the complex absorbs light, and that's what results in that deep royal blue color. It's direct visual proof of Werner's theory in action. Now here's a really powerful application. Cyanide is so deadly because its ions binds to the iron atom, which is at the heart of a vital enzyme in our cells. And this blocks the enzyme from working. But the antidote, it works by using the exact same principles of coordination chemistry. So here's how it works. First, as you can see on the left, the cyanide ligand forms a very, very stable complex with the iron in your enzyme, basically stopping it completely. Then the antidote is introduced. Now, this antidote molecule is an even more attractive ligand for the cyanide. So what happens is a ligand swap. The antidote literally steals the cyanide ion away from the enzyme, forming an even more stable complex. This frees up the enzyme to start working again, and the new harmless complex is safely removed from the body. It's really a life-or-death competition between ligands. Okay, let's tackle a common counterintuitive example. Imagine you have a cobalt ion with a +3 charge, CO3+. Your first instinct might be to say, okay, it just needs 3 chloride ions, 3 Cl-, to form COCl3 and become neutral. And you know what? From a simple charge balancing point of view, that makes perfect sense. But actually, the cobalt-3 ion has a much stronger demand. Its secondary valence, its coordination number, is 6. It needs to form bonds with 6 ligands to be stable, and it doesn't really care about their charge, so it will happily bond with 5 neutral ammonia molecules and just 1 chloride ion. For the metal, satisfying this coordination number of 6 is the #1 priority. So let's do a quick recap of what we've learned. First, the core idea. Metals have 2 valencies. Primary for just balancing charge, and the super important secondary for fixing the number and geometry of ligands. Second, our mental picture, the planetary system, with the metal as the sun and the ligands locked in fixed orbits. And third, the real-world impact. From explaining simple color changes in the lab all the way to being the basis of life-saving antidotes for poisoning.
So if you can just keep these 3 things in your mind, the core idea of 2 valencies, that planetary system analogy, and one real-world example like our copper solution, I promise you'll find that this whole topic of coordination compounds becomes much, much lighter for your exams. You will have the confidence to tackle any question that comes your way.